Now we will define very important properties of any vector field, which is differentiability of the vector field. As introduction, we can, for instance, we take two trivial examples of manifold, which is sphere and plane. And because we choose this trivial example because it's visual. We can imagine, using our human imagination, we can found for higher degree of manifold with higher dimension, it will be more difficult to visualize it. So for the sphere, at each point there is plane which is tangent to this sphere at that point. So the tangent field is just a plane at each point. The sum or the set of all plane with a tangent plane, we call it vector field. So for the plane, the tangent field is exactly the same, identical on the plane. And let's now look for, because they are vector space as we found previously, the tangent, the vector, they are vector space. For example, any tangent field is a vector space, so there is basis for each one. And there is, from the theory of vector spaces, we need to choose a basis in a way that this basis should be linearly independent. We don't have any problem. We don't have any problem at each point because by definition the manifold is locally Euclidean. So that means there is an open subset around each point of this manifold. In a way we can find coordinate xi, for example. So, and these coordinates are continuous and infinitely differentiable. That means I can differentiate with respect to it. So d over dxi. This d over dxi should, and we see later why we can assure that they should form a basis of the tangent field. For example, if I take any tangent vector of this tangent field, it could be written as in terms of this basis d over dxi with the component vi. But generally I can choose any basis, not necessarily this basis, arbitrary basis. For example, let's call it ej. Then the same vector could be written with other component with respect in this basis eg. So the rule of transform. So this vector has component in the first basis, which is d over dxi, and other component in the other vector basis, which is ej. And we see later that how we can change from the component of the first field of the first basis to other component to the other basis. So now, what is the differentiability? We return back to the main question. What is the differentiability of a vector field? We say the vector field is differentiable if and only if these components are differentiable. This is the definition. Now we need to make sure that why we can choose this d over dxi as basis of the tangent field, which is a natural question. The answer, we return back to the main definition of chart. For example, if I have manifold, at each point there is open subset neighborhood, we call it neighborhood U, for example, and there is one-to-one map associated each point of this open subset with another point in open subset in Euclidean of the same order of the manifold are they, and we call this if so there is this is one-to-one map, and we see there is mathematical theorem that prove that any one-to-one map has an inverse if and only if the determinant of the Jacobian is not zero, non-vanishing determinant. So the Jacobian dy over dxi has no vanishing determinant. By other word, the component dyi over dxi are linearly independent, and this is why we can choose d over dxi as basis of the tangent field. And now we return back. So how we can choose the coordinate xi in a way that I can assure that there is basis of the tangent vector at each point. Here they use a word that this is good coordinate or not. So it is good coordinate if the d over dxi are exist. So they form basis of and linearly independent. So such that they form a vector, a basis of the tangent field. And here we can give an easy example, which we talked about previously, about the good coordinate or not. For example, if I take about sphere, a sphere, is it a good coordinate to choose theta and phi or not? Is it a good coordinate or not? Actually, it is not good coordinate system. Why? Because we see that previously that and here we are talking about there is two problems at when theta equals 0 and theta equal pi, and also there is problem when phi equal constant. Let's say when phi equals 0, because when theta equal 0 there is line in the plane, in the Euclidean associated plane, in the Euclidean coordinate system. There is plane. Sorry. So there is at theta equal 0. I have, for example, I have x2 equal 0. This is line. And I have also problem when phi equal constant. At these 2 points, the partial derivative are not defined. So the coordinate system theta phi are not good one, because we cannot find using them a basis of the tangent vector such that d over dxi, for example, are linearly independent.